In this video, I would like to explore why the tangent function is called tangent, from the Latin word touch. What we are going to do is create a diagram on the unit circle in the xy plane, so this is the circle of radius 1. I'm going to situate our computation here in the first quadrant, but if you'd like, you could repeat this for the second, third, or fourth quadrants. Okay, let me grab a random point in this first quadrant. How about this one? We can connect that point to the origin. That's going to form a radius for our circle, so we know it has length 1. Whatever angle we are opening here with the positive x-axis is what we will refer to as theta throughout the rest of our computation. Okay, given that this is a point on the unit circle forming angle theta here, its x and y coordinates are cosine of theta, sine of theta. Okay, let's drop a line which is tangent to the circle through that point. That looks like this. Notice that this line is perpendicular to the radius. It's kind of like spokes on a wheel. So that means that the angle that we're opening up here, both here and here, those are both right angles. The radius has slope sine theta over cosine theta because that's rise over run as we move from the origin out to this point. So if this slope is sine theta divided by cosine theta, and this line segment is perpendicular to that radius, we know that the slope of this line segment is the negative reciprocal. So this line segment here, the line which is tangent to our circle, has a slope which is negative cosine theta divided by sine of theta. Okay, with that information, namely a point and the slope, we can write down the equation for this tangent line. What I'm going to do is point slope form. It's going to be standard point slope form, and then I'm going to do some rearrangements just to put it in a really nice form. Okay, so point slope form is the variable y minus the known y coordinate of the point you've chosen. So the y coordinate for this point is sine of theta. Okay, so y minus known y coordinate equals the slope, that's negative cosine of theta, divided by sine of theta, times x minus the known x coordinate, that's going to be x minus cosine of theta. Okay, that's point slope form. What I'm going to do now is multiply both sides by the sine of theta. So that will give me y sine of theta minus sine squared. And then on the right-hand side, we're just going to cancel out that sine of theta. Let me now distribute the negative cosine of theta. Let's write negative x cosine of theta plus cosine squared. We can bring this term to the left and this term to the right to write x cosine of theta plus y sine of theta equals cosine squared plus sine squared. But by the Pythagorean identity, cosine squared plus sine squared is 1. So let's write that here. Okay, this was the starting form for our line, and now I've rearranged it to x cosine theta plus y sine theta equals 1. All right, every xy coordinate on this line has to satisfy this statement. In particular, the two points I'm interested in are the x-intercept and the y-intercept. So let's find the x-intercept first. I'm going to call this capital X 0. So to find the x-coordinate of the x-intercept, we zero out the y-coordinate. That's going to cause this term to vanish. So we're left with x cosine of theta plus 0 equals 1. Right? That tells me that this x-coordinate down here is 1 over cosine of theta, but it's probably more fun to call that secant of theta. Okay. Go ahead and anticipate what the y-intercept will be. It's just based on sort of a symmetry of the x and y coordinates here. What do you expect? And what I would expect is if capital X pairs up with 1 over cosine, then capital Y will pair up with 1 over sine. And that is the case. So let's find 0y. That is going to mean 0 out the x coordinate, leaving us with capital Y sine of theta is 1. So as expected, the y-intercept up here is 1 divided by sine of theta, that's cosecant theta. Okay. I think this is fun because we're looking for some explanation of why the tangent function is called tangent, but along the way, in this diagram, we are also finding geometric meaning for the secant and cosecant functions, and as we'll find out in a few minutes, the cotangent function as well. Okay, let's take a little break. I'm going to step aside, pause if you need to write any of this down, think over the steps that we went through. And then when I come back, I'll have erased everything and we will move on to tangent and cotangent. We are building up our understanding of this tangent line. We know that the x and y intercepts can be described with the secant and cosecant functions. Next, I would like to take this line segment and break it into two pieces in a very natural way. So this piece here and this piece here. Let's start with this one here. Whatever its length is, let's call that capital L. Let's find that. So what is capital L? That is the distance from this point to the x-intercept. You might think, okay, distance formula, but there's a faster way. Do you see it? Notice what we have here is a right triangle. So let's just use the Pythagorean theorem. We can say that the radius squared, that's 1 squared, plus this missing quantity we're looking for, so L squared, equals the hypotenuse squared. That's going to be secant squared. Okay. You might immediately know what the solution to this is. If you don't, let me talk you through it. Look at this Pythagorean identity up here. What happens if you divide all three terms by cosine squared? Okay, so cosine squared divided by cosine squared is 1. 1 over cosine squared is secant squared, so that's here and here, which means sine squared divided by cosine squared should match up with L squared, and that's what we have. So sine squared over cosine squared partners up with L squared. That means L squared is tangent squared. Another way to say that is from the Pythagorean identity, we can get that tan squared is secant squared minus 1. Okay, we can square root both sides safely because we are in the first quadrant. So in the first quadrant, tangent is positive. So this length is tangent of this angle theta. That would also be true in the third quadrant, but in the second and fourth quadrants, you have to be a little bit careful because tangent is negative. So similar diagrams in the second and fourth quadrant would need you to have that the length is negative tan of theta to make it positive. Okay, so that is the length of this line segment. Take a moment and anticipate what the length of this line segment is. So we'll call that little l. Instinctively, what do you think it's going to be? And then let's pause and see if you can verify your prediction. I'll come back and finish the computation. Okay, let's see how you did. Once again, we have a right triangle here, so we can use the Pythagorean theorem. I will say that little l squared plus 1 squared equals the hypotenuse squared, which is cosecant squared. Like that. Just like a minute ago, we have an identity that we derive from the main Pythagorean identity, this time by dividing each term by sine squared. So sine squared divided by sine squared is 1 squared. 1 divided by sine squared is cosecant squared. That means that this L squared term should correspond to cosine squared divided by sine squared. That's going to be cotangent squared. Since we're in the first quadrant, just like before, we can take the square root of both sides to say that that length is cotangent of our angle theta. Same remarks about the signs in the second, third, and fourth quadrants. That wraps up this demonstration. I hope you enjoyed how seeing the circle together with its tangent line gives us a geometric way to interpret all 6 trig functions. So we've got cosine, sine, secant, cosecant, tangent, and cotangent. Back to our opening question, why is a tangent function called tangent? Now you can say the tangent function measures the length of a line segment which is tangent to the circle. So this line segment here has length tan of theta. Okay, thank you for your attention.